Hi, in this video I am going to solve the problems related to Lecture 1 on Basic Linear Algebra. Below this video you will find the link to the PDF file containing these problems as well as the link for these notes that you see on the display right now in PDF and in GoodNotes format. Okay, now let us start solving the problems. Okay, let us solve the first problem. We're supposed to write out a 2 by 3 matrix A with entries little a sub ij, where these entries are defined by a set of relations which are defined here. We're supposed to add I and j together if the absolute value of I minus j is equal to 0. We are supposed to add 2 times of I to j if this condition is met, absolute value of I minus j is equal to 1. And finally, we need to write the I index plus 2 times the j index if the absolute value of I minus j is equal to 2. And then, since this matrix is a 2 by 3 matrix, the general form of this matrix is of this form. It is A11, A12, and A13. A21, A22, and A23. Yes? So now we need to calculate each one of these entries one by one. So for the case of A11, I index is 1, J index is also 1, so I index minus J index is 0, and the absolute value of that one is also 0. So it means that for this entry here, I have to use the first rule. The first rule tells me that I need to add the I and j indices together. Here I and j indices are 1 and 1, so the answer would be 1 plus 1. Now let us go to the next entry here. It's 1, 2. I index is 1, j index is 2. The difference between these two, I minus j, is negative 1. But the absolute value of I minus j in this case is 1. So it means that for this entry I have to use this middle relation, and this tells me that multiply the I index by 2 and add it to the j index. Okay, so I will multiply the I index, which is 1 by 2, and add it to the j index. And when I go to the next entry, the I index is 1, the j index is 3. The difference between them is negative 2, but the absolute value of that is positive 2. So it means that for this entry I have to use this rule. Yes, so it means that I need to write the I index plus 2 times the j index. So the I index in this entry is 1, the j index is 3, so I need to multiply it by 3. And then when I go to the next one here, which is A21, the difference between I and j indices here is 1. Here is positive 1 actually, the I index minus j index. So again I have this condition satisfied, so I need to use this rule. I need to multiply the I index by 2. The I index in this case is 2, and then add it to the j index, which is 1. But for the next case I and j are equal, so again I have to use the first rule. And then I need to add I and j indices together. So here it becomes 2 plus 2. And finally, for the last one, I will have the I index and j index satisfying again the middle one. So here the I index is 2, the j index is 3. So I subtract them, it becomes negative 1. Absolute value of negative 1 is equal to 1. So I need to multiply the I index by 2 and add it to j index. Yes. And then finally, I simplify everything here, so it becomes 2, 4, 7, 5, 4, and 7. Okay, so that is the solution to this problem. Okay, now problem B. Let A be a square matrix of order 10. So A is a 10 by 10 matrix. The entries A sub ij are defined using these relations. A sub ij is defined to be 0 if the I index is less than the j index. This entry is defined to be 1 if the I index is greater than the j index. And finally, this entry is defined to be this 1 over I squared plus j if the indices are the same. And then we're supposed to calculate this double sum. These aij's are the entries of this matrix, and the I index, which is the row index, runs from 1 to 10, but 10 is also the order. And j also goes from 1 to 10, 10 is again the order. So it means that this double sum is actually adding up all the entries of the matrix. So we need to calculate the sum of all the entries in this matrix. To visualize the situation better, we can see that this is something, we have a matrix A. This matrix is a square matrix of this form, in which the main diagonal is this one. So you have the entries above the main diagonal, because do you remember, when we say I is less than j, it's here. All the entries above the main diagonal, all the entries here have the I index less than the j index, and all the entries here has the I index greater than the j index. So if I is less than j, so the entries are 0. So let me write a big 0 for here. So it means that what you see above the main diagonal, everything is 0. And then when I go below the main diagonal, every entry is equal to 1. So let me write a big 1 to show that every entry below is 1. And of course, there are some 10 entries on the main diagonal, because this is a 10 by 10 matrix. I am supposed to add all these numbers, but adding these numbers is super simple because that's just 0. Adding these numbers are also easy. We need to add these 10 numbers and then see how it goes. Okay, how many numbers are there? There are 10 numbers, and they are sitting on the main diagonal. So on the main diagonal, you know that I index is equal to j index. So aij on the main diagonal is equal to a sub I, because these two indices are the same. So in this formula, instead of j, I can also plug I, then I will get this is equal to 1 over I squared plus I. Okay, so if the sum of the entries on the main diagonal is equal to a11 plus a22 plus a33, and then I continue until the very last, which is a10, 10, and then I put a comma not to confuse myself here. So 10 is the I index, and 10 also again is the j index. But now aii is 1 divided by I squared plus I. So a11 is nothing except that 1 divided by 1 squared plus 1. A sub 22 is 1 divided by 2 to power 2 plus 2. A sub 33 is 3 to power 2 plus 3. And this continues until I reach to 1 over 10 to power 2 plus 10. Of course, adding these numbers, there are 10 numbers, 10 fractions that I want to add up. It's not a big deal, but my motivation of writing this is that you can realize that this is a telescopic sum, so you can do this easily without needing to use the calculator at all. So let me just explain how. If you see this generic term a sub I can write it in this form. I can write a sub I is equal, of course, to 1 over I squared plus I. But in the denominator, I can factor an I out. It becomes I times I plus 1. In the numerator, I can write, instead of 1, I can write I plus 1 minus I divided by I times I plus 1. Yes, but then I can write it as I plus 1 divided by I times I plus 1 minus I divided by I times I plus 1. And then here you see that this I plus 1 and this I plus 1 are gone. These two are gone. So what is left for me is 1 over I minus 1 over I plus 1. So what we realize is that any expression of this form can be written as a difference of 1 over I minus 1 over I plus 1. Okay, so now I need to calculate A11 plus A22 plus A3 3 up to A1010. So what can I do? A11 is 1 divided by 1 to power 2 plus 1. But this is the same expression, instead that the only difference is that instead of I have 1. So I can plug 1 here instead of I. So this becomes 1 over 1 minus 1 over 1 plus 1, which is 1 over 1 minus 1 over 2. And the next one, A22, is 1 over 2 to power 2 plus 2, which becomes 1 over 2 minus 1 over 2 plus 1. So what I am doing here, I am plugging 2 instead of I will get this, and this becomes exactly 1 over 2 minus 1 over 3. And the next one, 833, for the same reason you can continue, you reach to 1 over 3 minus 1 over 4. And if I continue this list, for example, I reach to A99, this also becomes 1 over 9 minus 1 over 10. Why? Because A99 means that I is equal to 9. So if I put 9 here, it becomes 1 over 9. If I put 9 here, it becomes 1 over 10. And finally, the last term, which is A10 comma 10, for the same reason, it becomes 1 over 10 minus 1 over 11. But my goal is to add all these numbers, okay, which are equal to these numbers. But adding these numbers is very simple. It's like a telescope. It becomes smaller and smaller. Numbers are canceling each other. So you see 1 over 2 negative here will be cancelled by this positive 1 over 2. But this 1 over 3 negative will be cancelled by this positive 1 over 3. Minus 1 over 4 will be cancelled from 1 over 4 that is coming next. And this will continue this cancellation. So 1 over 9 is already cancelled with the previous term. Minus 1 over 10 will cancel this one. But there are 2 terms left. One of them is the very first one, and the last one is the very last one. Yes, the next one is the very last one. So if I add them, it means if I add them together, then this means that A11 plus up to A1010 is equal to 1 over 1 minus 1 over 11. And this is very simple to calculate, so it's become 10 over 11. Yes. Finally, the sum that I was looking for, the double sum Aij, I goes from 1 to 10, j goes from 1 to 10, is the sum of all these entries. The sum of the entries on the main diagonal is 10 over 11. The sum of entries above the main diagonal here are all 0. The sum of the entries below the main diagonal is 45. Why is that the case? Because this matrix is a 10 by 10 matrix, so how many entries are there? Exactly 100. But 10 of them are sitting on the main diagonal, so if I subtract 10 from 100, it becomes 90. And so I need to divide it by 2, because half of them are the entries above the main diagonal and half of them are the entries below the main diagonal. So if I divide this by 2, it becomes 45. So 45 zeros are there, 45 ones are here. So the 45 zeros gives me the sum equal to 0. 45 ones give me the sum of 45. Yes. So then it means that I need to add 45 times 1 plus 45 times 0. So the answer is 45, 10 over 11. So that would be the answer to this problem. Okay, problem C. Matrix A with entries A sub ij, where A sub ij's are defined according to these rules. They are equal to alpha squared minus 3 alpha j plus 2j squared if the I index is greater than the j index. And they are defined to be 2 times the I index plus the j index, provided that the I index is less than or equal to the j index. So this matrix is assumed to be an upper triangular matrix of order 3. We are supposed to determine the value for alpha. Okay, so since this is supposed to be a 3 by 3 matrix, so in general a 3 by 3 matrix has this form, yes? So it is A11, A12, A13, A21, A22, A23, and finally A31, A32, and A33. This is a generic form of a 3 by 3 matrix. And then this is supposed to be an upper triangular matrix. So it means that if you consider this main diagonal, yes, below the main diagonal there are 3 entries. All of them have to be equal to 0. Yes. We don't know what's happening for these entries or even the entries on the main diagonal. But because this is supposed to be an upper triangular matrix, this should be guaranteed that these 3 entries are equal to 0. So then what should I do? So it means that I put A1, A21 equal to 0. But what is A21 in this case? The I index is 2, the j index is 1, so the I index is greater than the j index, so this will follow this rule. And the j index is 1, so I replace the j index with 1. So this gives me alpha squared minus 3 alpha plus 2 is equal to 0. I'm supposed to find alpha. I can use PQ formula, ABC formula, or even simpler, I can factorize it. So I put an alpha here, and I ask myself that I need 2 numbers whose sum is minus 3 and the product is positive 2, so those numbers are simply found to be minus 1 and 2, and this is equal to 0. Now the product of 2 numbers is equal to 0, so either this one is 0 or that one is 0, so this implies that alpha is equal to 1 or alpha is equal to 2. So these 2 values guarantee that this entry is 0, but that's not enough. I have to force that this entry should also be equal to 0. So I will have A32 equal to 0. Here again, this is the I index, this is the j index, so the I index is still greater than the j index. So what I need to do, I need to go here and replace the j value with the j index, which is 2 in this case, and equate it to 0. So then it becomes alpha squared minus 6 alpha plus 8 is equal to 0. Again, instead of using PQ formula, I can simply factorize it as alpha minus 2 and alpha minus 4. Yes. The product of these 2 numbers is positive 8, and then the sum of these 2 numbers is negative 6. So this gives me alpha is equal to 2 or alpha is equal to 4. Okay? So far, alpha equal to 1 is not acceptable because this makes this one 0 but not this one. Alpha equal to 4 is not acceptable because it only makes this one equal to 0, not that one. But we also have to check the next one, which is the last one in this case. A sub 31 should also be equal to 0. Here, the I index is 3, the j index is 1. So I index is again greater than j index, so I need to use this fact again. I need to use this rule again. So then it becomes alpha squared minus 3 alpha plus 2 equals to 0. Why? Because here the j index is exactly 1, so if I replace it with the j index, I will get the same equation. So this means that I can solve it as before, and I will get alpha equal to 1 or alpha equal to 2. But I want to have these three conditions simultaneously, so it means that I need to find the intersection between these answers, and then you realize that alpha equal to 2 is in all of them. So the answer to this problem is simply alpha is equal to 2. Okay, so that is also the solution to this problem. Okay, now in this problem, part D, two 5 by 5 matrices A and B are given to us, and then we're supposed to calculate these sums. In these sums we have the entries of matrix A, we have in general entries of matrix B, and a bunch of chronicle deltas. Yes? So the point of this exercise is to practice your understanding about the chronicle delta. Okay, so let us calculate this one. Of course, if I want to calculate this is not a big deal. So for example, one way to deal with this is just expanding the sigma in its full form, and then use the definition of the chronicle delta. Okay, so for example, I can calculate the first one in this way. I can expand this sum and write 1 for k, so it becomes A1 1, and then delta 1 2, and then I replace k with 2, the next number, so it becomes A1 2 delta 2 2, and then the next one would be A1 3 delta 3 2, and finally A1 4 delta 4 2. Yes, but then you realize that based on the definition of the chronicle delta, this is 0 because A1 and 2 are different. This is equal to 1 because the indices 2 and 2 are the same. Again, for the same reason, this is 0. The indices are different. The indices are different. This is also 0. And then what you get is that the answer is simply A1 2. Yeah, so that's the normal way of doing things. But I prefer you to learn what I told you in the previous session. So I see this delta. There are two indices k and 2. K, which is one of the indices, is the counter of this sigma, and the second index 2 is in the range of the counter of the sigma. So whenever this happens, I can simply eliminate delta. I can eliminate sigma as well, but the point is that wherever I see k, the counter, I replace it with the second index. So when I eliminate these two, then there is one place that I can see k. I am supposed to replace this k with the second index. Yes, and I will get A1 2. And that one A1 2 is exactly the answer that I get here. Okay, so let me practice this idea in this exercise. So number 2. Here what I have is a double sum, and then I have Aij delta J3. Okay, so in principle, if I want to make everything as I told you, I interchange these two sums first, and this is possible. Do you remember that in the previous session we showed that if we have double sums, we can interchange them? Okay, so what I do first, I write this or imagine it to be the sigma over I first, and then the sigma over j second. Then I will have A sub ij delta j3. Now look here. I have a sum, and this delta depends on the counter of this sigma. Okay, so what I can do, I can eliminate delta and this sigma, but wherever I see j left, I replace it with the second index of my delta, which is 3. So imagine if this is gone, 1 sigma and aij are left, and then I am supposed to replace j with 3. So then I will get sigma, I goes from 1 to 2, and I will have I3. But then of course there is no delta dependence, so I have to expand my sigma by replacing I with 1 and then replacing it with 2 and adding them together. So then it becomes A1 3 plus A2 3. But then if I go to matrix A, A1 3 is the entry on the first row and the third column, so it is 0. This one is on the second row and the third column again, so that is 1. So the answer is 0 plus 1, which is 1. Okay? Now let us do the number 3. So in number 3, I have 3 sigmas. Okay, let us see how it goes. Here, the sigma, which is close to delta, depends on j, and j is one of the indices here. So what I can do, I can eliminate these two, but I need to be careful, of course, that the second index is in the range of this sigma. Okay, the range of this sigma is from 1 to 5. The second index is k. Is it in the range? Yes, because you see the k itself runs from 1 to 5, and the range of j is also from 1 to 5. So it doesn't matter which value of k we have, this k value is always in the range of this sigma. So it's important. This point is important. So I eliminate this and I eliminate this, and in what is left, I replace every j with k. But there is no j left when I eliminate this. So what happens is just simply this expression, it becomes equal to sigma k goes from 1 to 5, sigma I goes from 1 to 5, a I k. So let me just repeat it quickly. So you see this sigma depends on one of these counters, j, and the second counter k is in the range, so I can eliminate these two, but in what is left I need to replace j's with k. But when I do this, there is no j left, so that's done. Yes, so this means that this is the end of this problem here. But of course then you need to interpret this. What is this expression? These are the entries of matrix A where the I index, which is the row index, runs from 1 to 5, and the k index in this case, which is sitting for the column index, runs again from 1 to 5. So in principle, and this matrix is 5 by 5. So this is the total sum of the entries of this matrix. So the sum of all entries of matrix A, which I have already calculated. If I haven't done any mistake, it should be 44. Okay, now let us go and check number 4. So number 4, let us analyze the problem. I have the double sum and I have one delta, and then the sigma sitting next to delta depends on m. The counter is m, and m is exactly one of the indices. So I can eliminate these two, but I need to be careful. Is the second index of my delta in the range of the counter? The answer is yes, because the second index is L. Is L in the range of sigma here? You might say that I cannot answer it because I don't know L, but yes, you do, because L goes from 1 to 5, and regardless of the value that you have it here, it's always in the range of the counter of this sigma, because M is also running from 1 to 5. So everything is in order, so I can eliminate these two. But wherever M is left, that M should be replaced by the second index, which is L in this case. Okay, so what I do, I would write sigma L goes to from 1 to 5. Okay, so in principle AL and AM2 are left. Look, if I eliminate this and I eliminate this, these two and this sigma are left, so that I have written here, but this is not correct. I need to replace m, if left, with L. Yes, and then one m is left here, so I replace it with L. I replace it with L. Hopefully you understand what's going on. And now there is no other point. I have to expand this sigma. So this becomes A11, A12 plus A12, A22, A13, A32, A14, A34, A32. I made a mistake. And A14, A42, and A15, A52. Yes, so I am expanding this sigma. So L is 1, L is 2, L is 3, L is 4, and L is 5. And always I have 1, 2, 1, 2 everywhere. Okay, and then you can go and read these numbers from the matrix. So A11 is actually 2 multiplied by A12, the first row second column, which is -1. Then I have A12, yes, which is -1 multiplied by A22, which is 2, plus A13, 13 is 0 multiplied by A32, which is 2, which is 1, and then A14, so let me double check these things not to make mistake. A11 is 2 multiplied A12 is -1, that's correct, and then I will have A12, yes, which is again -1 multiplied by A22, which is 2, that's also correct, but A13, the first row, this one is 0 again, and multiplied by A32, 32 is 1, that's also correct, but then A14, the first row fourth column is 4 multiplied by A42, yes, the fourth row second column, is 5, and then the first row fifth column is 0, fifth row second column is -1. So then this becomes -2 plus 20, so it becomes 16. Hopefully I haven't made any mistakes, but at least my point is not calculating this, is writing this sigma. Okay, you can double check my calculations. Okay, now let us go to this more interesting part here. So here we have 1, 2, 3, 4 sums, and then we have a bunch of numbers in front of the sigma. 3 of them are delta functions. Okay, so you can see that, for example, what I can do, I can eliminate this delta, which depends on L, and with this sum. Okay, so let me write them step by step so that you can understand it. Okay, the first thing I will eliminate, so let me cross them with a color here. Yes, I eliminate this delta here, yes, with this sigma, including that counter. Okay, so what is left for me is 3 sigmas. I goes from 1 to 5, J goes from 1 to 5, and then K goes from 1 to 5. And then what are left for me are AIK, BJL, delta K3, delta IJ. But when you eliminate a delta with the sigma corresponding sigma, there shouldn't be any track of this counter left. But you see this L is there still. Here I have an L. The point is that you need to replace L everywhere with the second index of your sigma, which is 4. So what I need to do is to eliminate this L and write 4 instead. Hopefully you understand what's going on. Okay, now look here. what can I do now? For example, this delta here depends on k and 3. This delta sigma depends on k. So again, I can eliminate this delta and this sigma. So what is left for me? What is left for me is two sums. I goes from 1 to 5, sigma, j goes from 1 to 5. And then what is left for me is aik, bj4, and delta ij. But this is not completely correct, because what I have done, I have eliminated this delta and this sigma. You see, there shouldn't be any notion of k. There is no k here. What I need to do, I need to go here and see that k has to be replaced with 3 everywhere left. Yes, so what I do, I clean this k and put 3 instead. Okay? Now again, I can see that I have a delta here depending on I and j, and I have 2 sigmas, but that this sigma depends on j and this is close to this. So what I can do, I can eliminate again, I can eliminate this delta and this sigma. Okay, so let us see what is left. Let us repeat it again. So sigma I from 1 to 5 is left. A I3 and BJ4 are left, yes? But because I am eliminating the sigma over j, I need to go and look to the delta. The second index is I, so there is no j, there shouldn't be j left. J's should be replaced by I. So it means that I go here and I take this I, j away and write I. Yes? And now everything is in order. So I expand this sigma. So this becomes A 1 3, B 1 4, A 2 3, B 2 4, A 3 3, B 3 4, A 4 3, B 4 4, and then finally a 5 3, B 5 4. Yes? And then of course the rest of it is easy. I can leave it for you. So these are numbers coming from the matrix. What are they, by the way? They are all sitting on the third column. The first row, the second row, the third row. So I go to the fourth column here, for example. Yes, so those numbers are 4, 7, 2, and -1 and 3. But then if you go to B, these are the numbers all sitting on the fourth column again, from 1, 2, 3. So all of them. So it means that I need to... So sorry, that was the third column. Yes, the third column. So I need to go to the third column. And then I have the fourth column for B. So the third column should be multiplied by the fourth column. So 0 should be multiplied by 3, it gives me 0. 1 should be multiplied by -7, it gives me -1. 0 should be multiplied by 1, it gives me 0. The next one gives me 5. The next one also gives me 5. And I add them together, it gives me 3. Yes? So the answer to this at the end would be 3. Okay, now we go for the last part, but because there is no enough space here, so let me move to the next page. So here I am supposed to calculate this expression, but if you compare it with the part 5, you can see that everything is the same except these two sigmas. This sigma I goes from 1 to 5, here sigma I goes from 3 to 5, and sigma for j goes from 1 to 5. Here sigma j goes from 1 to 3. But these two sigmas are exactly the same, and what you see here is exactly here. So, but let me explain everything again. So, to make sure that you understand it quite well. So here, I consider this delta I with L and 4, and then there is a sigma with counter L. Yes? The second index 4 is actually in the range of this sigma. So everything is in order. So it means that I can eliminate this L, this delta L4 with this sigma, but the price that I need to pay is to switch L to 4 everywhere. Why 4? Because 4 is the second index. So what I do, I rewrite this expression. So this becomes sigma I goes from 3 to 5, and then sigma j goes from 1 to 3, and then I have sigma k goes from 1 to 5. Yes, if I just want to copy and paste everything, it becomes a I k b j l delta k3 and delta ij. But I told you that you need to replace L with 4 everywhere, and then there is only one place that I have L, so I have to replace it with 4. Yes, so I erase it and write 4 here. Okay, now another time. So you see another delta here with this count sigma, which have the same counter as one of the indices here. Okay, but the important thing is that the second index 3 is in the range of the counter of this sigma. So what I can do again, I can eliminate this delta with this sigma with the same counter, but the price that I need to pay is to replace k with 3 everywhere. So what does it mean? It means that it becomes sigma I goes from 3 to 5, sigma j goes from 1 to 3, then I will have a ik bj4 delta ij. Again, as I told you, I need to replace k with 3 everywhere, so I am not allowed to write this k, so I clean it and write 3 instead. Okay, but now if you want to do the same thing here, you need to be careful. Can I eliminate this delta with this sigma and switch j to I everywhere? So here the indices are I and j. The indices of my delta are I and j. If I want to use this delta to eliminate this sigma, then it means that wherever j is left, in principle, I should change it to I. But this can be only done if the second index, which is I in this case, should be in the range. Yes, but this is not always the case, because you see the index I runs from 3 to 5. Yes, if this I happens to be 3, yes, then it is in this range. But if I is 4 and 5, then it is not in this range. So it means that this is not as simple as before to eliminate them. So I need to consider two cases. Yes, so it means that I continue. I would say that if I is 3, let me write this sum for I equal to 3 and for more than 3. So assume that I is 3, then this becomes sigma j goes from 1 to 3 a, but instead of I put 3, and then the second one is also 3. Then I will have bj4, then I have delta 3j. Yes, so I wrote this expression for I equal to 3, but then I can write plus sigma. Now I can run I from 4 to 5, and then I will have sigma j equal to 1 to 3, ai3 bj4, and then I have delta ij. So I considered the case of I equal to 3 separately. Okay, but now what can I do here? So you see this expression delta 3j depends on this sigma. So can I eliminate this with that one? There is yes, because the second index is 3 and 3 is in the range. So I can eliminate this one and this one, but the price that I need to pay is to replace j with 3 everywhere. So then what happens for this first term? Let me repeat it again. This and this are eliminated. So what is left for me is a 3, 3, be j4, but I am supposed to replace j with 3 everywhere. Why? Because 3 is in the range of my sigma. So then it means that I need to clean this j and write 3 instead. Yes, so this becomes just 3. But what happens for this sigma? In this sigma, this j runs from 1 to 3 and I runs from 4 to 5. So the minimum value for I is 4, but the maximum value for j is 3. So it means that this is not possible for I and j to be equal at all. So this delta that appears here is always equal to 0. So this means that this sum will vanish, and this is left for me. Okay, and now if you want to go back here, you have 833. This is your 833 here, and then this is 834, the third row, fourth column. It is 1. So you need to multiply these two, so it becomes 0. So it becomes 0 times 1, and the answer becomes 0. Okay, so hopefully you understand how you need to deal with this delta, chronicle delta, inside some sums. Okay, let us go to the next problem here. So the next problem is also very simple now, because I'm supposed to calculate this double sum. Yes, and then I have A as a matrix, a square matrix of order 100. So you see the indices run from 1 to 100 here, from 5 to 100 here, and then I'm supposed to calculate this. Okay, so let me rewrite this one for you. So sigma I goes from 5 to 100, and then sigma j goes from 1 to 100, and then I have A sub ij, delta I sub ij. Okay, so this delta depends on the indices I and j, and this sigma close to this depends on this j. So in principle, it might be possible that I can eliminate these two. If I want to make sure that this is indeed the case, I need to consider the second index I. Is the second index I in the range of this sigma? The answer is definitely yes, because I runs from 5 to 100, and it doesn't matter which one of these values I takes, it is still in this range. So this means that this is completely valid, and I can eliminate this. So let me change my color. I can eliminate this and with that one. So what happens is that I am left with a sigma I goes from 5 to 100, and then I will have Aij. But I told you, when you do this, you need to replace j with I. So this means that this j should be written as I. So I clean it and I write I. Of course, you don't need to write and clean, but I'm writing it because I want you to make sure that you understand it better. So what I need to do is just calculating this sigma. So if I want to calculate this sigma, what can I write instead of AII? This is AIJ, so AII means that I can replace j with I again. So this becomes sigma I goes from 5 to 100, and then this becomes 1 over I squared plus I. But that is exactly the sum that we have in this problem, if you remember. Yes, so that was exactly the way that I calculated this. I mentioned that this is a telescopic sum, but the problem here, in this problem, I starts from 1 to 10, but in my problem here, it goes from 5 to 100, even though that's a very big number of fractions, but because of telescopic sum we can do it easily. So if you remember, I don't repeat it again, so you can just refer to the solution of that problem. So I goes from 5 to 100, and then this becomes 1 over I minus 1 over I plus 1. Yes, so instead of this expression, you can easily check, as I did it in that exercise, that this is equal to that expression. But now this sum means what? You need to put 5 and then 6 and then 7 until you reach to 100. Yes, so what should I do? So this, if I put 5, it becomes 1 over 5. I replace I with 5. This becomes 5, this becomes 6. And then the next one becomes, if I put 6, it becomes 1 over 6 minus 1 over 7. The next one becomes 1 over 7 minus 1 over 8. And if I continue until I reach to 100, it becomes 1 over 100 minus 1 over 101. But then what happens again is like a telescope. This one cancel this one cancel this one, this will cancel the next one, this will be cancelled by the previous one. So this term and that term are the only terms that are remained. Yeah, so this becomes 1 over 5 minus 1 over 101. So then the common denominator is 505, so it becomes 101 minus 5. Yes, and the answer would be 96 divided by 505. So that would be the answer to this problem. Okay, good. Now we go to the last problem. In the last problem, so you can probably do it in two different ways, but let me write it in this form. If I want to do it, I will calculate this in this form. Instead of delta squared, I will write delta ij, another delta ij. So I am multiplying delta ij by itself 2 times. Yes? This is possible. But then I can use the same trick. I can use this delta to eliminate this sigma. Is that possible? Because this sigma depends on j, you need to consider the second index. Is the second index always in the range of the first index here? Yes, because j goes from 1 to 20, I also goes from 1 to 20. So that's always the case. So it means that I am on the safe side. I can eliminate this delta with this sigma. The price is that wherever j is left, I need to replace it with I. So this becomes sigma. I goes from 1 to 20, and then I am left with delta I. Okay, but this is very simple now because delta I is 1 and I am calculating, so this is equal to delta 1 plus delta 2 plus delta 3 up to delta 20. But all of them are equal to 1, so 1 plus 1 plus 1 up to 120 summands. Yes, and then this becomes 20.